The most terrifying thing James Webb has discovered isn't a galaxy, a black hole, or a colossal explosion deep in space. It's the possibility that we've fundamentally misunderstood the true scale, pace, and history of the universe we live in. The farther James Webb looks back toward the Big Bang, the more it finds objects that shouldn't exist, as if the universe itself is ignoring the very rules we've used to explain it. If you want to understand why these discoveries are shaking the foundations of modern cosmology, stay with me until the end of this journey. Get ready. Let's begin. You already know Hubble. The pillars of creation, those towering columns of gas and dust, glowing in colors almost too beautiful to be real. That image landed on magazine covers, classroom walls, and the screensavers of millions of Americans who had never once thought about astronomy. For 30 years, Hubble was humanity's eye on the cosmos orbiting above Earth's blurring atmosphere, delivering images that made the universe feel close enough to touch. But here's what nobody told you. Hubble was blind, not metaphorically piant, physically, fundamentally, irreversibly blind to the most important light in the universe. To understand why, you need to know one thing about light and movement. When a fire truck races away from you, the pitch of its siren drops. The sound waves stretch out as the source moves, arriving lower and longer than they started. Light does the same thing. The universe has been expanding since the Big Bang, carrying every galaxy away from every other galaxy. And as that ancient light travels across billions of light years of expanding space, its wavelengths get stretched, pulled from visible light into infrared radiation. Wavelengths the human eye cannot detect. Wavelengths Hubble's instruments were never built to capture. The oldest galaxies in the observable universe, the ones that formed when the cosmos was only 600 to 700 million years old, don't arrive as visible light anymore. By the time that light completes a 13 billion light-year journey to us, expansion has shifted it entirely into the infrared. Hubble was staring directly at the most ancient era of cosmic history and seeing nothing, not because the universe was hiding, because Hubble simply didn't have the right eyes. That is where the James Webb Space Telescope comes in. And calling Webb a bigger Hubble is like calling a submarine a fancier rowboat. They are not the same category of machine. Webb's primary mirror spans 6.5 meters. Hubble's is 2.4 meters. Those numbers sound close until you think about what a mirror actually does. It collects light. And collecting area scales with the square of the radius? Webb gathers roughly 6 to 7 times more light than Hubble. That is not an incremental improvement. That is a different instrument in every meaningful sense. The mirror is built from 18 hexagonal segments of beryllium, an ultralight metal chosen because it holds its precise shape even at extreme temperatures. Each segment is coated in a microscopically thin layer of gold, not silver. Gold reflects infrared wavelengths more efficiently than silver. And every single material choice on this telescope was made for one purpose: to see what no instrument has ever seen. But the mirror alone doesn't explain what makes Webb so revolutionary. The real answer is temperature. Infrared radiation is, at its core, heat. Any warm object radiates it, including the telescope itself. If Webb's detectors were even slightly warm, they would be overwhelmed by their own thermal glow, completely unable to distinguish faint signals from the distant universe. So, Webb needed to be cold, not cool, not refrigerated, extraordinarily, precisely, almost impossibly cold. NASA positioned Webb at the second Lagrange point L2, a gravitational balance point 1.5 million kilometers from Earth, always in the direction directly opposite the Sun. At L2, Earth and Sun are permanently on the same side, allowing a single sunshield to block both at once. That sunshield has 5 layers, each one as thin as a single human hair. together spanning an area roughly the size of a tennis court. The sunlit side reaches temperatures near 85 degrees Celsius. The cold side, where the telescope's mirrors and detectors sit, drops to approximately negative 233 degrees Celsius, 40 degrees above absolute zero. At that temperature, the telescope's own infrared emission becomes negligible. The ancient light of the universe can finally be heard above the noise. Hubble could detect a candle burning at the distance between New York City and Washington, D.C. Webb, from its frozen position at L2, could detect that same candle through a brick wall. And because light takes time to travel, distance equals time. Every extra billion light years of depth is another billion years peeled back from cosmic history. Webb's infrared sensitivity pushes that window all the way back to within a few 100 million years of the Big Bang itself. A moment in time no telescope had ever reached before. Webb launched on December 25, 2021. After nearly 2 decades of development and a total program cost of approximately $10 billion, it reached L2 and achieved full operational status by July 2022. Its designed lifetime is 10 years, though the precision of its launch trajectory preserved enough propellant to potentially extend operations to 20 years. It observes across wavelengths ranging from 0.6 micrometers in the near-infrared to 28 micrometers in the mid-infrared, a range engineered specifically to capture the redshifted signatures of the universe's first structures. NASA spent 20 years and $10 billion building this machine, and engineers still lost sleep knowing a single micrometeorite, a grain of cosmic dust, no larger than a sand grain, could damage one of its mirror segments. The universe, it turns out, charges a high price for its secrets. Webb is not an upgrade. It is a new sense, a biological leap for a species that had reached the hard limit of what visible light could reveal. And now, finally equipped with infrared vision capable of piercing 13 billion years of cosmic time, humanity pointed it at the sky. So, what did the most expensive telescope in human history see the moment it first opened its eyes? The answer left even the most seasoned astrophysicists speechless. In December 1995, astronomers did something that sounded almost reckless. They pointed the Hubble Space Telescope at a tiny, unremarkable patch of sky near the Big Dipper, a region with no known stars, no known galaxies, nothing of obvious interest, and they left it there for 10 consecutive days. 10 days of collected light aimed at what looked like pure darkness. When the image came back, it contained roughly 3,000 galaxies. Every single smudge of light in that frame was an entire galaxy, each one holding hundreds of billions of stars. That image, the Hubble Deep Field, became one of the most consequential photographs in human history. It permanently reset humanity's sense of scale, but it also set an expectation, a logical one, a reasonable one, an expectation that turned out to be completely wrong. The galaxies Hubble captured in its deep field images that were young, the ones from the early universe, less than 1 billion years old, looked exactly as theory predicted. Faint, small, irregular, lumpy blobs of star-forming gas still in the process of assembling themselves. That made perfect sense. The universe was young. Gravity had barely had time to pull matter together. Structure takes time to build. You don't expect a city to exist before anyone has laid a single brick. The scientific consensus was settled, and sensible early galaxies were primitive, messy, and incomplete. On July 11th, 2022, President Biden stood in front of a screen at the White House and unveiled the first full-color science image from the James Webb Space Telescope. The target was a galaxy cluster designated SMACS 0723, located at a right ascension of 7 hours 23 minutes, declination -73.4 degrees, at a redshift of 0.39, approximately 4.6 billion light-years away. The image had been assembled from 12.5 hours of exposure time. 12.5 hours, compared to Hubble's 10 days, and the depth was comparable. That alone was staggering, but it was what the image actually showed that stopped people cold. Behind the cluster, magnified and bent into arcs of light, were galaxies from the universe's earliest era objects, whose light had traveled more than 13 billion years to reach Webb's mirrors. And they were not faint. They were not simple. They were not the primitive blobs that every cosmological model had predicted. They were bright, structured, complex, some showing clear spiral formations, organized arms of stars, the kind of architectural detail that our own Milky Way took billions of years to develop. Professor Garth Illingworth, an astronomer at UC Santa Cruz who had led the original Hubble Deep Field program, looked at the Webb image and said it was unlike anything he had seen before. This was not a young scientist encountering something new. This was one of the people who built the previous benchmark, telling the world that the new data did not fit the framework he had spent decades constructing. The mechanism behind the image requires a moment to unpack because it is one of the most elegant tools in observational astronomy. The galaxy cluster. SMACS 0723 sits between us and those ancient background galaxies. A cluster that massive warps the fabric of space-time around it, bending the paths of light traveling from objects behind it. That bent light gets redirected toward us, and in the process, amplified. The cluster acts as a natural lens not made of glass, but made of gravity itself. Einstein predicted this effect in 1915 as a consequence of general relativity. It took a century and a $10 billion space telescope to turn that prediction into a precision observational instrument. The effect is similar to looking through the thick, curved base of a heavy glass light, passing through bends and magnifies what's on the other side. Webb used SMACS 0723 as exactly that, a cosmic magnifying glass built by physics, revealing galaxies that would otherwise be too faint and too distant to study in any detail. And what those galaxies revealed broke something in the standard model. Spiral structure in a galaxy is not simple to produce. It requires differential rotation across a disk of gas and stars. The gravitational influence of dark matter halos settling into stable configurations, feedback from generations of star formation, regulating the system over time. Cosmological simulations consistently showed that this kind of organized complexity needed several billion years to emerge. Yet Webb was showing it in galaxies that were less than 1 billion years old. The bricks were already arranged into cathedrals before anyone had time to lay the foundation. What made the image even more remarkable was what Webb extracted from it beyond the visual. Webb's instruments performed spectroscopic analysis on the galaxies in the same exposure, breaking their light into its component wavelengths the way a prism splits sunlight. From that analysis, astronomers could read the chemical composition of those ancient galaxies, their temperatures, their velocities, even the presence of specific elements in their atmospheres. All of it from a single observation session. Hubble could show you what early galaxies looked like. Webb could tell you what they were made of and how fast they were moving. One of the details that emerged from that analysis was the presence of cold gas filaments threading between some of those ancient galaxies' streams of raw material flowing between them like rivers of fuel. That cold gas is significant. It is the ingredient galaxies consume to form stars. The presence of those filaments at such an early epoch suggested these galaxies were being actively fed, supplied with material at a rate fast enough to explain their unexpected size and complexity. The universe, apparently, had a supply chain operating far earlier and far more efficiently than anyone had modeled. The uncomfortable question that followed was unavoidable. If galaxies were already this complex, this structured, this massive at less than 1 billion years old. What had been happening in the hundreds of millions of years before? That what process, invisible to every telescope that came before Webb, had already done the heavy lifting? It was like opening a mailbox and finding a newborn infant who already knew how to drive. Theoretically impossible, but the evidence was sitting right there in front of you, sharp and undeniable, captured in 12.5 hours of starlight. The observable universe is estimated to contain approximately 2 trillion galaxies. Webb's first image covered a patch of sky a fraction of the size of a full moon. And in that sliver, the laws governing cosmic evolution were already showing cracks. But this was only the first image. When scientists began systematically surveying the sky, they found something even stranger: massive galaxies that could not exist, that were existing anyway. Every house ever built follows the same sequence. You dig the foundation first, then you pour concrete, then you frame the walls, then, and only then, do you put on the roof. You cannot skip steps. You cannot build the 10th floor before the first floor exists. The physics of construction simply will not allow it. The standard model of cosmology works exactly the same way. The lambda-cold dark matter model, lambda CDM. The framework that has guided cosmology since the 1990s describes a universe that builds itself in strict sequential order. After the Big Bang, the cosmos was filled with thin, hot hydrogen gas. Over hundreds of millions of years, that gas slowly cooled. Dark matter, which feels gravity but not radiation pressure, began clumping first, forming invisible scaffolding. Ordinary gas fell into those dark matter halos and gradually, patiently, collapsed under gravity to form the first small stars. Those stars then clustered into small galaxies. Small galaxies merged over billions of years to form larger ones. The process was slow, methodical, governed by well-understood physics. A galaxy as massive as the Milky Way, containing hundreds of billions of solar masses worth of stars, required billions of years to assemble. That was not an assumption. That was a prediction derived from decades of observations, simulations running on the world's most powerful supercomputers, and a theoretical framework tested against virtually every dataset available. Then the JADES survey opened its eyes. JDS, the JWST Advanced Deep Extragalactic Survey, is one of the most ambitious observational programs in the history of astronomy. It covered a region of sky spanning 25 square arc-minutes, accumulating over 700 hours of telescope time to reach the faintest, most distant objects Webb could detect. When astronomers processed the data, they found 6 galaxies sitting at redshifts greater than 7.5. That redshift corresponds to a universe less than 700 million years old. In some cases, less than 550 million years old. Each of those 6 galaxies contained between 10 billion and 100 billion times the mass of the Sun in stars alone. Several of them matched or exceeded the current stellar mass of the entire Milky Way. The Milky Way took over 13 billion years to reach its current size. These galaxies did it in less than 700 million years. The lead researcher on the study, Ivo Labbé, along with colleagues publishing in Nature in 2023, called them the universe breakers. That phrase was not hyperbole for a press release. It was the actual scientific assessment. The probability of these galaxies existing within the lambda CDM framework was, in their words, extraordinarily low. The model had no mechanism to produce them. To understand exactly why, you need to understand what star formation actually requires. A star is born when a cloud of gas becomes dense enough and cold enough that gravity overwhelms the thermal pressure trying to push it apart. The cloud collapses. At the core, pressure and temperature rise until hydrogen fusion ignites. A star turns on. But this process is self-limiting in a critical way. the moment that star begins radiating energy. It pushes back against the surrounding gas with its own radiation pressure and stellar winds. It heats the material around it. It drives gas outward. That feedback mechanism slows and eventually halts further star formation in the same region. The galaxy has to wait for that gas to cool again, fall back in, and begin the cycle over. It is a built-in brake on the entire process. Because of that brake, the Lambda CDM model predicts that even in the most favorable conditions, a galaxy can convert at most around 10% of its available gas into stars. 10% is considered extraordinarily efficient. Most galaxies do far less than that. The universe breakers required 50 to 100% efficiency. Every last gram of available gas would have had to collapse into stars almost simultaneously, with essentially no feedback, no cooling delay, no self-regulation of any kind. Asking for that from standard physics is like asking a bakery to convert every pound of flour in its storage room into finished bread in 10 minutes, not just fast, but a violation of the temperature, timing, and thermodynamics of the oven itself. The physics of the process simply does not allow the output the data was describing. The theoretical physics community immediately began searching for explanations. Several hypotheses are currently being tested. One proposes that the dark matter in the early universe was not cold, as the standard model assumes, but warm, composed of lighter particles that created smaller, denser halos, potentially allowing gas to collapse and form stars on faster timescales. Another hypothesis involves population 3 stars, the theoretical first generation of stars in the universe, formed from pure hydrogen and helium with no heavier elements to complicate the process. These stars were predicted to be extraordinarily massive, possibly hundreds or even 1,000 times the mass of the Sun. Burning so intensely, they lived only a few million years before exploding. A burst of such stars could in principle produce enormous stellar mass in a very short window. The problem is that population 3 stars have never been directly observed. They remain theoretical. Webb is currently the only instrument that might eventually see them, but the evidence has not arrived yet. The third possibility is the most uncomfortable one, that Lambda CDM itself has a flaw, that the standard model, which has successfully predicted so much of what we observe in the universe, is missing a physical ingredient. Something that made the early cosmos behave far more violently and efficiently than any simulation has been able to reproduce. That possibility carries weight far beyond galaxy formation. Lambda CDM is not just a description of how galaxies grow. It is the mathematical foundation for predictions about dark matter, dark energy, the large-scale structure of the universe, and the ultimate fate of the cosmos. If it fails here, the failure does not stay contained. It spreads. Theoretical physicists working in cosmology right now are in a position something like an engineer who spent 50 years designing and building a bridge, then watched a fully loaded freight truck barrel across it before the first support cable was even installed. The truck was heavier than the bridge, and it was moving fast. The JADES survey covered 25 square arc-minutes of sky. The full sky contains roughly 148 million square arc-minutes. What JADES found in that tiny sliver: 6 impossible galaxies, each one a direct challenge to the standard model, raises an obvious and deeply unsettling question about what the rest of the sky might contain. But those massive, mysterious galaxies were only the opening act. Inside them, JWST detected a chemical signature that could not exist, something that, by all theoretical accounts, had no business being there. Every atom of oxygen in your lungs right now was forged inside a dying star. That is not poetry. That is nuclear physics. When the Big Bang occurred, 13.8 billion years ago, the explosion produced exactly 3 elements in any meaningful quantity: hydrogen, helium, and trace amounts of lithium. That was it. The entire periodic table beyond those three: every carbon atom in your DNA, every iron atom in your blood, every oxygen atom you are breathing at this exact moment, none of it existed. The universe started almost completely empty of the ingredients that make chemistry, planets, and life possible. The elements we are built from had to be manufactured, and the only factory capable of producing them was a star. Inside a stellar core, gravitational pressure and temperature are high enough to fuse lighter elements into heavier ones. Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into oxygen, neon, magnesium, and silicon. In the most massive stars, this chain continues all the way to iron. When a massive star exhausts its fuel and collapses, the resulting supernova explosion is violent enough to forge elements heavier than iron and scatter everything outward into surrounding space at thousands of kilometers per second. That expelled material, enriched with carbon, oxygen, nitrogen, iron, becomes the raw ingredient for the next generation of stars and, eventually, planets. Carl Sagan put it simply: we are made of star stuff, but that process has a timeline. A star must be born, live out its life, and die before it can contribute a single atom of oxygen to the universe around it. A star like our Sun burns for approximately 10 billion years. A massive star, the kind capable of producing a supernova quickly enough to matter in the early universe, burns hotter and faster, exhausting its fuel in a few million years. Even at that pace, the sequence is non-negotiable. You need the star to form first. Then it has to live. Then it has to die. Then its material has to disperse and cool. Then a new generation of stars and galaxies can form from that enriched gas. The whole process takes time, and in the early universe, time was the one thing in shortest supply. Which is why what JWST found in May 2024 should not exist. The galaxy designated JADES-GS-Z14-0 was confirmed in a paper by Carniani and colleagues, published in Nature in May 2024. It sits at a redshift of 14.32. That number translates directly to a cosmic age. The light from this galaxy left its source when the universe was only 290 million years old. At the time of publication, it was the most distant, spectroscopically confirmed galaxy ever recorded. Webb's instruments, specifically the near-infrared spectrograph and the mid-infrared instrument, NIRSpec and MIRI, analyzed the light from JWST and found an emission line at 88 micrometers, corresponding to ionized oxygen, doubly ionized oxygen, to be precise. The signature designated as O3, oxygen, unambiguous, confirmed by two independent instruments on the same telescope. Oxygen, in a galaxy that existed 290 million years after the Big Bang. 290 million years is, in the theoretical framework of lambda CDM, barely enough time for the very first stars to begin forming at all. Not enough time for those stars to complete their lives and explode. Not enough time for their debris to cool, collapse, and assemble into a second generation. Not enough time for that second generation to live and die and enrich the gas further. The oxygen in JADES-G-Z14-0 required all of that to have already happened. Multiple stellar generations, born, lived, died, enriched the surrounding medium, and seeded the material from which this galaxy then built itself, all within a window that theory said was barely long enough for the first star to switch on. The comparison is almost absurdly clear. Plant an oak tree today. 300 years later, someone finds a warehouse full of cut lumber, dried and stacked, with no living trees anywhere nearby. It is not just unexpected. It is structurally impossible unless there was already a forest no one knew about, doing its work long before anyone was looking. JADES-GS-Z14-0 itself is not small. Its stellar mass is approximately 500 million times the mass of the Sun, roughly 5 times 10 to the power of 8 solar masses. Its star formation rate, measured from the same spectral data, runs at approximately 20 solar masses of new stars formed per year. That is an extraordinarily high rate for any galaxy, let alone one that was assembled in less than 300 million years. Its physical diameter is estimated at around 1,600 light-years compact by galactic standards, but extraordinarily dense given how much stellar mass has been packed into that volume. The implications cascade outward from that single detection. If oxygen is present at a redshift of 14.32, then star formation, real, complete stellar generations cycling through birth and death, must have begun well before 290 million years after the Big Bang. The models that place the onset of star formation somewhere between 100 and 200 million years post-Big Bang may themselves be too conservative. The universe may have lit its first stars within the first 100 million years, perhaps even earlier, in a burst of activity so rapid and efficient that current simulations cannot reproduce it. This is where population 3 stars re-enter the picture. These are the theoretical first stars formed from pure primordial hydrogen and helium, with no heavier elements present to complicate the process. Because metal-free gas behaves differently under gravitational collapse, population 3 stars are predicted to have been extraordinarily massive, potentially reaching 100 to 1,000 times the mass of the Sun. Stars that heavy burn through their fuel in 1 to 3 million years and die in violent explosions, far more energetic than standard supernova. A burst of population 3 stars could in principle seed a large region of space with oxygen and other heavy elements in an extremely short time, potentially explaining what JADES-GS-Z14-0 is showing. The problem remains the same as before. Population 3 stars have never been directly observed. They are theoretical constructs inferred from first principles. Webb may eventually see them at redshifts above 20, in the absolute edge of the observable universe, but that data does not yet exist. What does exist is the oxygen line in JADES-GS-Z14-0. Confirmed. Published, peer-reviewed, impossible to explain without stellar generations that should not have had time to complete. Oxygen sits at atomic number 8 on the periodic table. 8 protons per nucleus, each one forged under conditions of unimaginable pressure and heat, then scattered across space in a dying star's final explosion, then gathered again by gravity into new clouds, new stars, new galaxies. Every breath you take draws in oxygen that traveled that entire journey across billions of years. The discovery in JADES-GS-Z14-0 means that journey started earlier than anyone calculated. The factories were running before the blueprints said the factory floor had been laid. Finding an electricity bill inside a house that hasn't been built yet. Nobody pays for power in a building that doesn't exist. And yet, the bill was there, printed, dated, real. Oxygen was not the only impossible thing hiding in the early universe. Deeper still, JWST spotted tiny red dots, and they were things that should not exist under any law of physics we know. At the center of the Milky Way, roughly 26,000 light-years from Earth, sits a black hole called Sagittarius A star. Its mass is approximately 4 million times that of the Sun. That sounds enormous until you compare it to the galaxy containing it. The Milky Way holds somewhere between 100 billion and 400 billion stars. Its total stellar mass is estimated at around 50 billion to 60 billion solar masses. Sagittarius A star, at 4 million solar masses, represents roughly 0.01% of that total. 1/10,000th of the galaxy's stellar mass, a rounding error, cosmically speaking. This ratio is not unique to the Milky Way. Astronomers have measured it across hundreds of galaxies in the nearby universe and found the same pattern repeating with remarkable consistency. Supermassive black holes at galactic centers typically contain between 0.1% and 0.2% of their host galaxy's total stellar mass. The relationship is so stable, so universal, that cosmologists built it into their standard model of galaxy evolution as a foundational assumption. Black holes and galaxies grow together, feeding and regulating each other through a process called co-evolution. The black hole influences star formation through its energetic outbursts. The galaxy's gas supply controls the black hole's growth rate. They keep each other in check, locked in a kind of gravitational partnership spanning billions of years. The ratio stays stable because the physics enforces it. There is also a hard physical ceiling on how fast a black hole can grow. When matter falls toward a black hole, it doesn't fall straight in. It forms a rotating disk of superheated gas, an accretion disk that radiates enormous amounts of energy as it spirals inward. That outward radiation exerts pressure on the surrounding gas, pushing it away from the black hole and limiting the rate at which new material can fall in. The point at which radiation pressure exactly balances gravitational infall is called the Eddington limit. It is a fundamental boundary set by physics, not engineering. A black hole cannot simply eat faster by trying harder. The radiation it generates in the process of eating pushes its food away. Then Webb found the little red dots. Beginning with early survey data and confirmed across multiple independent studies, including a catalog published by Matthey and colleagues in the Astrophysical Journal in 2024. Covering more than 300 objects from the JWST Primer Survey, astronomers identified hundreds of compact, extremely red, intensely luminous objects scattered across redshifts from 4 to 9. That range corresponds to a period when the universe was between 600 million and 1.5 billion years old. The objects were small. Visually, they appeared as faint red smudges, barely resolved even by Webb's extraordinary optics. Hence, the name Little Red Dots. Spectroscopic analysis confirmed what their luminosity alone had suggested. These were active galactic nuclei, AGN, black holes at the centers of young galaxies, actively accreting matter at extraordinary rates. Labbe and colleagues, whose work on the universe breakers had already shaken the field, were among the first to flag the mass ratios coming out of the data. In some of these systems, the black hole's mass was not 0.1% of the host galaxy. It was not even 1% or 5%. In several confirmed cases, the black hole mass accounted for more than 30% of the total stellar mass of the galaxy surrounding it. Some measurements pushed toward 40%, 30 to 40%, against a universal baseline of 0.1% in the nearby universe. That is not a statistical fluctuation. That is not measurement uncertainty. That is the relationship between black holes and galaxies being 300 to 400 times more extreme than anything observed in the modern cosmos in objects that, by definition, had far less time to reach that state. The Eddington limit makes this worse, not better. Think of drinking through a straw submerged in a thick milkshake. You can only pull so hard before the pressure differential collapses the straw, or the suction simply can't overcome the resistance of the fluid. The harder you try, the more the physics pushes back. A black hole consuming matter generates radiation that acts exactly like that resistance. Pull too hard, and the outward pressure exceeds the inward gravitational pull. the accretion shuts itself off. This is a physical law, not a guideline. Some of the little red dots appear to be accreting at rates 100 to 1,000 times above the Eddington limit, not modestly exceeding it, violating it by orders of magnitude in ways that no existing accretion physics model can fully account for. Several mechanisms have been proposed. Chaotic or magnetically arrested accretion, where strong magnetic fields trap and compress infalling material into dense streams that bypass the normal radiation pressure equilibrium. Super Eddington accretion through an extremely thick, optically dense disk that traps its own radiation, preventing it from escaping and pushing back on the infalling gas. Each of these is theoretically possible in extreme conditions. None of them has been definitively confirmed as the operating mechanism in these objects. What makes the little red dots stranger still is their behavior across different wavelengths. Standard active galactic nuclei are bright in X-rays. The hot plasma in the accretion disk and the corona above it emit powerful X-ray radiation. This is one of the primary ways AGN are detected and classified. The little red dots are bright in infrared. They are faint in X-rays. Some are nearly invisible to X-ray observatories. One explanation is that they are buried under dense clouds of dust and gas that absorb X-rays before they escape, while allowing infrared radiation to pass through. Another possibility, more radical, is that these objects represent a fundamentally different mode of black hole accretion that the standard AGN model does not describe. A third possibility has been raised by a minority of researchers and cannot yet be dismissed. Some of the little red dots may be primordial black holes, objects that did not form from collapsing stars at all, but were created directly in the extreme density fluctuations of the Big Bang itself, long before any galaxy or star existed. If primordial black holes are real and abundant, they would provide a natural explanation for why some black holes in the early universe are so disproportionately massive relative to their host galaxies. They started massive before the galaxy even formed around them. This connects to the broader question of black hole seeds, the initial objects from which supermassive black holes grew. 3 scenarios are currently under investigation. The first black holes formed from the remnants of massive population 3 stars, the same theoretical first-generation giants discussed in the context of the oxygen crisis. This pathway is too slow to explain the masses observed in the little red dots. The second direct collapse black holes, where an entire massive cloud of primordial gas collapses directly into a black hole without passing through a stellar phase, producing an object of 10,000 to 100,000 solar masses from the outset. This is physically possible, but requires very specific environmental conditions. The third primordial black holes from the Big Bang itself, still unproven, still contested, but no longer dismissible given what Webb is showing. If the ratio between black hole mass and galaxy mass was radically different in the early universe, the entire co-evolution model, the framework describing how black holes and galaxies shaped each other across cosmic time, needs to be rewritten from the beginning. Not updated, rewritten. A 6-month-old infant who weighs as much as their father is not experiencing accelerated development. The doctors don't call that a miracle of growth. They call it a sign that something in the fundamental biology needs to be re-examined from the ground up. These anomalous black holes are just a symptom of a deeper disease. The cosmological model we have trusted for 30 years is beginning to unravel from within. Lambda CDM is not just a theory. It is the backbone of modern cosmology, developed and refined through the 1980s and 90s. The lambda cold dark matter model describes the entire history of the universe from the first fraction of a second after the Big Bang to the large-scale structure visible today using just 6 fundamental parameters, 6 numbers. From those 6 numbers, Cosmologists can derive the temperature fluctuations in the cosmic microwave background, the distribution of galaxies across hundreds of millions of light years, the abundance of hydrogen and helium in the universe, and the rate at which cosmic structure assembled over time. The model has been tested against dataset after dataset and has passed with extraordinary precision. It is, by any reasonable measure, one of the most successful theoretical frameworks in the history of science. Its picture of the early universe is specific, clear, and, it turns out, increasingly difficult to defend. According to Lambda CDM, the early universe was a place of slow, inefficient, gradual construction. Dark matter halos formed first, small ones merging over long timescales into larger ones. Gas cooled slowly into those halos and formed stars at modest rates. The brightest, most massive galaxies came late, assembled through many generations of mergers over billions of years. The model predicts a specific distribution of galaxy brightness at any given epoch, a luminosity function that describes how many galaxies of each brightness level should exist at any given redshift. At redshifts above 8, where the universe was less than 650 million years old, that luminosity function predicts a sharp drop-off. Bright, massive galaxies should be rare, very rare. Webb saw something else entirely. In 2022, Harikani and colleagues published a catalog in the Astrophysical Journal Supplement series identifying 55 galaxy candidates at redshifts above 10 from the first available JWST data. 55 objects where the model predicted almost none. In 2023, Michael Boylan-Kolchin published an analysis in Nature Astronomy examining the statistical tension between what Lambda CDM predicted and what Webb was actually observing at redshifts above 8. The tension sat at 2 to 3 sigma, meaning the probability of this discrepancy arising by chance within the standard model was less than 0.1%. The specific star formation rates the rate at which these galaxies were converting gas into stars per unit of existing stellar mass ran 3 to 10 times higher than the model's predictions. This is not a case of 1 or 2 anomalous objects that can be explained away as outliers. It is a statistical trend. Hundreds of galaxies, surveyed systematically across multiple independent programs, consistently appearing brighter, more massive, and more efficiently star-forming than Lambda CDM says they should be. The early universe, according to the data Webb is returning, was not a slow, low-efficiency construction site. It was a blast furnace, dense, fast, violent, and productive at a level the standard model has no mechanism to explain. The population forecast analogy makes the scale of the problem clear. Imagine a city planner projecting that a new urban area will reach 1 million residents after 100 years of steady growth. 5 years in, the census comes back showing 10 million people already living there, with growth rates still accelerating. The planner does not simply adjust the growth curve and move on. Something fundamental about the underlying assumptions about how cities form, about what drives population growth, about what resources and conditions are actually available, has to be reconsidered entirely. Lambda CDM is not wrong in the way a broken clock is wrong. It works. It predicts the cosmic microwave background with stunning accuracy. It correctly describes the large-scale structure of the nearby universe, the clustering of galaxies, the abundance of light elements. The model is not broken everywhere. It is missing something that made the early cosmos behave with a level of productive violence that no current simulation reproduces. An ingredient possibly related to how dark matter behaves on small scales, possibly related to feedback processes between black holes and their host galaxies, possibly something not yet named that turns the early universe from a slow assembly line into something closer to an explosion happening in slow motion. Several directions are being actively investigated. self-interacting dark matter, a variation in which dark matter particles interact with each other through a new force, altering how halos form on small scales, and potentially allowing denser, more productive star-forming environments to emerge earlier. Early dark energy, a proposed form of energy that was significant in the first few 100,000 years after the Big Bang, modifying the expansion history in ways that could shift the timing of structure formation. Changes to the reionization history, the epoch when the first stars and galaxies ionized the surrounding neutral hydrogen, which could affect how efficiently feedback suppressed star formation in the early universe. None of these modifications has yet been confirmed. Each one, if validated, would require revisions to other parts of the model. Science is not a monument. It is a living structure, and it corrects itself. When Newtonian mechanics failed to account for the precession of Mercury's orbit, the answer was not to abandon physics. The answer was general relativity, a framework that contained Newton's equations as a special case and extended beyond them into previously uncharted territory. Lambda CDM may be heading toward a similar revision, a new framework that preserves what the old model got right and adds what it was missing. Nobody said that process is comfortable for the people who spent 40 years building the original structure. A perfect map of a city that suddenly reveals an entire unmapped district is still a good map. It is just not a complete one. What Webb is doing, systematically and relentlessly, is charting the unmapped district. Every galaxy that appears where Lambda CDM said there should be none is another data point that narrows down what the missing ingredient must look like. The model is not collapsing. It is being forced to grow. But the growth required may be more radical than anything cosmology has had to absorb since the discovery of dark energy itself. But the chaos of the early universe is only one piece of the picture. When we step back and look at the entire cosmos at its largest possible scale, what emerges is not order, but a vast web of matter with voids so enormous and so empty, they produce a specific kind of dread that is very difficult to put into words. Most people, when they think about the universe, picture something like a snow globe, galaxies scattered more or less evenly in every direction, distributed across space the way stars appear distributed across the night sky. Random, yes, but roughly uniform. No giant gaps, no dramatic clusters, just a steady and continuous spread of light and matter filling the cosmos in all directions. That picture is wrong, profoundly, structurally wrong. The actual architecture of the universe, revealed through decades of large-scale surveys and now being examined in unprecedented detail by Webb, looks nothing like a snow globe. It looks like a spider's web, or more precisely, like the three-dimensional structure of neurons in a human brain, a vast network of dense filaments connecting bright nodes with enormous dark spaces between them. Astronomers call it the cosmic web, and it is the largest known structure in existence. The Sloan Digital Sky Survey, which mapped the positions of hundreds of millions of galaxies across a large portion of the observable universe, produced images of this structure that remain among the most disorienting in all of science. Galaxies do not spread evenly through space. They cluster along thin filaments of dark matter threads, stretching hundreds of millions of light-years in length, only a few million light-years thick, and pile up at the nodes where those filaments intersect, forming massive galaxy clusters containing thousands of individual galaxies. Between the filaments and the nodes, there is almost nothing. These are the voids, regions of space so empty, so vast, so genuinely devoid of matter that the word empty barely does them justice. The cosmic web forms because of dark matter, cold dark matter, which doesn't interact with light or ordinary matter except through gravity, began clumping in the early universe along the slight density variations left over from the Big Bang. Those clumps became gravitational anchors, pulling ordinary gas toward them and concentrating matter along the paths of least gravitational resistance, which happen to form the filament structure we observe. The process is self-reinforcing. More matter along a filament means stronger gravity, which pulls in more matter, which strengthens the filament further, while the voids between them drain of material over billions of years. The result is a structure that looks, at the largest scales, like a network of soap bubbles. All the matter sits on the thin walls and edges of the bubbles. The interiors are empty. Not entirely empty. Voids contain a small number of galaxies, so-called void galaxies that formed in relative isolation, starved of the raw material that their counterparts in filaments and clusters had in abundance. Void galaxies are strange objects, typically low in mass, slow in their star formation, and structurally different from galaxies that grew up in denser environments. They are the hermits of the cosmos, sitting alone in regions where the dominant force is not gravity pulling things together, but dark energy pushing what little remains ever further apart. The most famous void in the known universe was discovered in 1981 by a team led by Robert Kirshner and published by Kirshner and colleagues. Before that discovery, astronomers knew voids existed, but assumed they were relatively modest in size gaps of tens of millions of light years, unremarkable in the broader structure of the cosmic landscape. What Kirshner's team found instead was the Bode's Void, located in the direction of the constellation Bode's, approximately 700 million light-years from Earth. The Bode's Void spans approximately 330 million light-years in diameter. Inside that volume, a sphere 330 million light-years across there, are roughly 60 known galaxies. Standard cosmic density would predict thousands. The void is not slightly underdense. It is catastrophically, almost incomprehensibly underdense. 330 million light-years of near-nothingness. A volume so large that the Milky Way's entire local group, the cluster of roughly 54 galaxies that includes our own, could fit inside it tens of millions of times over. The scale comparison that stops people cold is this one. The distance from Earth to the nearest large galaxy outside our local group is approximately 2.5 million light-years. That is the Andromeda Galaxy. The Bode's Void is 330 times wider than that distance. If the Milky Way sat at the center of the Bode's Void, the nearest neighboring galaxy would be 150 million light-years away. Radio telescopes capable of detecting galaxies at that distance were not developed until roughly the 1960s, which means that if we lived inside the Bode's Void, humanity would have had no way of knowing other galaxies existed until within living memory of people alive today. We would have looked out into an apparently empty universe and had no instrument sensitive enough to detect anything beyond our own isolated island of stars. The Bode's Void is not the only one. The universe is filled with voids of varying sizes, interlocked in a hierarchy of structure. Above the scale of individual galaxy clusters sit superclusters. Above superclusters sit the great wall sheets of galaxies spanning hundreds of millions of light-years. Above those sit the supervoids, regions of underdensity so extreme they influence the cosmic microwave background itself by allowing photons traveling through them to lose energy, creating faint cold spots detectable in all sky CMB maps. The KIDS, BOSS, and EBOSS surveys have confirmed the cosmic web structure out to redshifts approaching 2, mapping the filaments and voids across billions of light-years of cosmic history. The universe is not a filled container. It is a framework, a lattice of gravity-sculpted matter suspended in a sea of emptiness, where the emptiness is winning. The voids are growing. As dark energy drives the accelerating expansion of the universe, matter continues to drain from low-density regions toward the filaments and nodes, but the voids themselves expand faster than matter can refill them. Over cosmic timescales, the web becomes sparser, the voids wider. and the filaments thinner. A universe slowly sorting itself into increasingly concentrated islands, surrounded by increasingly enormous oceans of nothing. Webb's role in probing this structure goes beyond mapping. By observing galaxies inside and around known voids, galaxies that formed and evolved in environments starved of the dark matter scaffolding and gas supply that filament galaxies enjoy. Webb is testing how star formation, chemical enrichment, and structural evolution differ between cosmic environments. The early results are already showing that void galaxies at high redshifts behave differently from their counterparts in denser regions in ways that complicate the Standard Model's predictions about how environment shapes galaxy growth. The Webb is not just a map. It is an experimental laboratory with conditions that cannot be reproduced anywhere else. There is a question the structure of the cosmic web raises, but cannot yet fully answer a question about whether the universe's large-scale architecture is truly as uniform as foundational cosmology requires. That question will demand its own full accounting later in this story. For now, the Webb stands as it is staggering in scale, alien in structure, and populated by voids that dwarf anything in human experience. 330 million light-years of empty space. If the universe were a party, the Buddha's void would be the room nobody wants to enter. No food, no music, no light. And the room itself is larger than every other room in the building combined. Those voids are unsettling enough. But the truth is, more unsettling still, our own Earth may be sitting inside an enormous void right now. And that position is warping every cosmological measurement we have ever made. There is one number at the heart of all modern cosmology, one measurement that everything else depends on. Get it right, and you can calculate the age of the universe, the geometry of space, the fate of all matter and energy from the first fraction of a second after the Big Bang to the last cold remnant of the last dying star. Get it wrong, and every derived result, every timeline, every prediction, every model of cosmic evolution carries the same error compounded across 13.8 billion years. That number is the Hubble constant, designated H0. It describes the rate at which the universe is expanding. How many kilometers per second faster a galaxy is receding from us for each megaparsec of additional distance. It is the expansion rate of the cosmos, expressed as a single value, and it is the foundational parameter of modern cosmological science. Measuring it should be straightforward. In practice, it has become the most consequential unresolved crisis in astrophysics. Two independent methods exist for measuring the Hubble constant, each using completely different physics, each considered internally robust. The first uses the cosmic microwave background, the thermal afterglow of the Big Bang, detected across the entire sky and analyzed in extraordinary detail by the Planck satellite. By fitting the precise temperature fluctuations in that radiation to the standard cosmological model, physicists extract a value of 67.4 kilometers per second per megaparsec, with an uncertainty of plus or minus 0.5. The second method builds what astronomers call the cosmic distance ladder, a chain of overlapping measurement techniques anchored at each step by the previous one. Cepheid variable stars, whose pulsation periods are tightly correlated with their intrinsic luminosity, give precise distances to nearby galaxies. Those distances calibrate the brightness of Type 1a supernovae, which can be detected at far greater distances and used to measure recession velocities. The SH0ES team, led by Adam Rees and reporting in 2022, obtained a Hubble constant of 73.04 kilometers per second per megaparsec, with an uncertainty of plus or minus 1.04, 67.4 versus 73.04, a difference of roughly 8%. 8% sounds small. In this context, it is catastrophic. The statistical significance of that discrepancy accounting for the quoted uncertainties from both measurements, is 5.0 sigma. In physics, 5 sigma is the threshold for declaring a discovery. A 5 sigma discrepancy does not arise by chance. It means something is wrong in one of the measurements, in the underlying physics, or in the model connecting them. The simplest way to understand what 5 sigma means is this. Suppose two people measure your height. One measures from the floor up and gets 5 feet 10 inches. The other measures from the ceiling down and gets 5 feet 5 inches. Both insist their tape measures are accurate. Both insist their methods are sound. 5 sigma says the probability that this discrepancy is a coincidence or a random error is less than 1 in 3.5 million. It is not a coincidence. Something is genuinely different about the two measurements, and the physics of measurement itself is not enough to explain it. The options are stark. Either the physics of the early universe, encoded in the cosmic microwave background, is being misinterpreted, or the physics of the nearby universe, encoded in Cepheid distances and supernova brightnesses, contains a systematic error no one has yet identified. Or there is something in the universe itself, not in either measurement, that makes the local expansion rate genuinely different from the global rate. The third option is where the KBC Void enters. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie published a study mapping the density of galaxies in the universe within approximately 2 billion light-years of Earth. Their finding, which gave the void its name, was that the region around us is underdense, containing roughly 20% less matter than the cosmic average across a sphere approximately 2 billion light-years in diameter. If confirmed, this would make the KBC Void one of the largest underdense regions ever identified. The implications for the Hubble tension are direct. Inside a void, matter is depleted. Less matter means weaker gravitational pull on surrounding galaxies. With less gravity to restrain them, galaxies near the edge of the void flow outward more rapidly than average, carried not just by the global expansion of the universe, but also by the local gravitational gradient between the underdense interior and the denser material outside. To an observer sitting inside that void, sitting where Earth happens to sit, those outflowing galaxies appear to be receding faster than they would in an average region of the universe. The local measurement of the Hubble constant gets inflated, not because the expansion rate is truly different, but because the sample of galaxies used to measure it is not a representative sample of the cosmos. It is a biased sample, drawn from the peculiar neighborhood of a supervoid. Trying to measure the global temperature of Earth's atmosphere while standing in the middle of the Sahara Desert gives you a number. It might even be a precise number, but it is not the global average. The Sahara is an outlier, and standing inside it means every measurement you make is colored by that local condition, whether you know it or not. Webb has sharpened this problem rather than resolved it. Friedman and colleagues, publishing in 2024 using JWST data, measured the Hubble constant using alternative distance indicators, the tip of the red giant branch method and the carbon star method, designated TRGB and JAGB, and obtained a value of 69.96 kilometers per second per megaparsec, with an uncertainty of plus or minus 1.9. That sits between the Planck value and the SH0ES value, neither confirming nor eliminating the tension, but suggesting that the distance ladder calibration at its lowest rungs may carry some systematic uncertainty that Webb is beginning to resolve. The tension did not disappear. It changed shape. The deeper implication of the KBC Void, if it is real, and if it is truly 2 billion light-years in diameter, goes further than the Hubble tension. Every observation we have made of the local universe, every galaxy survey, every measurement of galaxy clustering, every estimate of the local matter density has been made from inside this potential void. If we are in an underdense bubble, we are not in a typical part of the cosmos. Our observations are systematically biased in ways that are difficult to fully quantify, because we cannot step outside the bubble and measure what we would see from a more average vantage point. It is a coloring on the lens we cannot remove, because we cannot take the lens off. Cosmology is trying to measure the velocity of the universe from a vantage point that may itself be moving in an unexpected direction. The vehicle making the measurement may be 2 billion light-years wide, but we are not only sitting inside a void we are being pulled. The entire Milky Way, together with 100,000 neighboring galaxies, is falling towards something hidden behind a curtain of space that we have only just begun to see. Most people know that Earth orbits the Sun. Most know the Sun is one of roughly 200 to 400 billion stars in the Milky Way. Some know that the Milky Way belongs to a small cluster of galaxies called the Local Group, about 54 galaxies bound together by mutual gravity, with the Milky Way and Andromeda as the two largest members. A smaller number know that the Local Group sits within a larger structure called the Virgo supercluster, a concentration of galaxy groups and clusters spanning roughly 110 million light-years. Almost nobody knows what comes next. And what comes next is one of the most staggering discoveries in the history of astronomy. In 2014, Brent Tully of the University of Hawaii and colleagues published a paper in Nature that redrew the map of our cosmic neighborhood entirely. Their method was not based on the positions of galaxies alone. It was based on their motions. Every galaxy in the local universe is moving carried by the expansion of space, yes, but also pulled and pushed by the gravity of surrounding matter. By mapping those velocity flows with precision, Tully's team could trace which galaxies were gravitationally bound to the same large-scale structure, flowing toward the same gravitational basin, and which were falling toward different attractors entirely. The result was a new definition of the supercluster to which the Milky Way belongs. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. The name was coined in collaboration with Nawa'a Napoleon, a native Hawaiian language expert and astronomer, chosen to honor the tradition of Polynesian navigators who crossed the Pacific by reading the stars. People who understood the sky as a map before any modern instrument existed. Laniakea spans approximately 520 million light-years in diameter 160 megaparsecs. It contains roughly 100,000 galaxies. Its total mass is approximately 10 to the power of 17 solar masses. To put that in context, the Milky Way has a mass of roughly 1 trillion solar masses, 10 to the power of 12. Laniakea outweighs the Milky Way by a factor of approximately 100 trillion. If the Milky Way were a single cell, Laniakea would be a nation-state. The Milky Way does not sit at the center of Laniakea. It sits at the outer edge, a peripheral member of a vast supercluster whose gravitational heart lies far away, in a direction that has been known for decades by a name that sounds almost mythological: the Great Attractor. The existence of the Great Attractor was first inferred in 1986 by a team of 7 astronomers: Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner, who became known informally as the 7 Samurai. They were studying the velocities of elliptical galaxies across a large region of sky and found something that should not have been there: a systematic deviation. Hundreds of galaxies, including the Milky Way itself, were moving in the same direction at roughly 600 kilometers per second relative to the cosmic microwave background frame. Something was pulling them. Something massive, located at a distance of approximately 250 million light-years, in the direction of the constellations Centaurus and Norma, 600 kilometers per second, on a highway. That speed would carry you from New York City to Los Angeles in approximately 7 seconds. The Milky Way has been moving at that velocity toward the Great Attractor for billions of years and has not arrived yet. The universe is that large. Identifying the Great Attractor precisely has been difficult for a specific reason. It sits almost exactly behind the plane of the Milky Way as seen from Earth. The disk of our own galaxy, dense with dust, gas, and stars, obscures roughly 20% of the entire sky in what astronomers call the zone of avoidance. Optical telescopes are effectively blind in that direction. The Great Attractor lies squarely inside it. What we know about it has been pieced together through radio wavelengths, near-infrared observations that partially penetrate the dust, and X-ray surveys that see through the galactic plane more effectively than visible light. Current understanding identifies the Great Attractor with a large galaxy cluster called the Norma cluster and a broader region of mass concentration in that general direction. But even the Great Attractor turns out not to be the final destination. Behind it, at a distance of approximately 650 million light-years, lies an even more massive concentration of galaxies and dark matter called the Shapley supercluster, the largest known concentration of mass in the observable universe within a few hundred megaparsecs. Laniakea is not just falling toward the Great Attractor. The Great Attractor itself is falling toward Shapley. Our entire local supercluster is one branch in a larger flow, a river joining a bigger river that is itself draining into an ocean. The iRosetta X-ray Telescope, launched in 2019, and ongoing surveys using near-infrared wavelengths are actively mapping the zone of avoidance, gradually lifting the curtain that has obscured the Great Attractor's full structure for decades. Webb is contributing to this effort at the level of individual galaxy spectroscopy, providing redshifts and stellar masses for galaxies in and around the obscured region with a precision that previous infrared instruments could not match. An important clarification: this motion does not contradict the expansion of the universe. The universe is expanding everywhere, carrying all galaxies apart from one another on large scales. But overlaid on that expansion are what cosmologists call peculiar velocities, motions driven by local gravity, by the pull of nearby concentrations of mass. Laniakea's infall toward the Great Attractor, and ultimately toward Shapley, is a peculiar velocity flow. The expansion of space does not stop this flow from happening. It simply means that at large enough distances, the expansion wins structures too far from Shapley to fall toward it. Within the age of the universe will never reach it, carried beyond gravitational reach by the accelerating expansion of space. Whether Laniakea will ultimately merge with the Shapley supercluster or be torn away from it by dark energy's relentless push depends on which force wins over the billions of years ahead. This motion, 100,000 galaxies, flowing at 600 kilometers per second toward a gravitational sink 250 million light-years away, is not a recent development. It has been happening for billions of years. It is happening right now. Every second, the Milky Way moves 600 kilometers closer to the center of Laniakea's gravitational basin. You cannot feel it. No instrument on Earth can detect it directly against the noise of Earth's own motion around the Sun and the Sun's motion through the Milky Way. But it is real, measurable by mapping the velocities of galaxies on scales no single telescope could previously achieve. We are not stationary. We are not even nearly stationary. We are passengers on a galaxy inside a supercluster, falling through space toward a gravitational attractor that took decades to find and is still not fully mapped, itself falling toward a larger structure beyond it, in a universe that is simultaneously expanding in all directions faster than any of this infall can ultimately overcome. We are being pulled by an enormous gravitational force, but at the same time, there is another force invisible, mysterious, comprising 68% of everything that exists, pushing back against all of it. And that force just did something nobody predicted. In 1917, Albert Einstein added a term to his field equations of general relativity. He called it the cosmological constant, represented by the Greek letter lambda. He inserted it deliberately as a mathematical counterweight to gravity, a repulsive term that would prevent the universe from collapsing under its own gravitational pull. At the time, the prevailing assumption was that the universe was static. Einstein believed it. The cosmological constant was his way of making the equations agree with that belief. In 1929, Edwin Hubble showed that distant galaxies are receding from us, and that more distant galaxies are receding faster. The universe was not static, it was expanding. Einstein, upon learning this, reportedly called the cosmological constant his greatest blunder. He removed it from the equations. It was no longer needed. For nearly 70 years, the cosmological constant stayed in the discarded drawer of physics. Then, in 1998, two independent teams studying Type 1a supernovae, Saul Perlmutter's Supernova Cosmology Project and Brian Schmidt's High-Z Supernova Search Team, which included Adam Rees, discovered something that overturned the entire picture. The universe was not just expanding, it was expanding at an accelerating rate. Something was driving galaxies apart faster and faster over time, working against gravity on cosmological scales. That something needed a name and a physical description. Lambda came back. The cosmological constant was resurrected, rebranded as dark energy. And Einstein's greatest blunder became one of the most important concepts in modern physics. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011. Dark energy, in the Standard Model, constitutes approximately 68% of the total energy content of the universe. Ordinary matter, everything made of atoms, everything we can touch, see or detect with any instrument, contributes roughly 5%. Dark matter accounts for about 27%. Dark energy, the dominant ingredient in the cosmos, is also the one we understand least. Its physical nature remains entirely unknown. The leading theoretical interpretation identifies it with the energy of the quantum vacuum, a baseline energy density that empty space carries simply by existing, arising from the constant creation and annihilation of virtual particle pairs at the quantum level. If dark energy is vacuum energy, it has one critical property: it is constant. It does not change with time. It does not evolve. The same energy density that drove acceleration a billion years ago drives it today, and will drive it 10 billion years from now, at precisely the same strength. In the equation of state language physicists use, this corresponds to a parameter called W equal to -1. Exactly -1. That is the prediction of the cosmological constant model constant. Static, immutable. In 2024, the Dark Energy Spectroscopic Instrument, or DESI, released its first-year data results. DESI, a spectrographic survey instrument mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, measured the spectra of 6.4 million galaxies and quasars, mapping their distances and recession velocities with extraordinary precision. From those measurements, it extracted the baryon acoustic oscillation signal, a characteristic scale imprinted in the distribution of galaxies by sound waves in the early universe, a standard ruler that allows cosmologists to measure the expansion history of the universe across billions of years. The results were published in April 2024 as Arfrinjev, preprint 2404.03002. The data did not agree with W equal to -1. When DESI's baryon acoustic oscillation measurements were analyzed alone, the tension with the cosmological constant reached 2.5 sigma. When combined with the cosmic microwave background and Type 1a supernova data from the Dark Energy Survey's 5-year sample, the tension reached 3.9 sigma, the best fit values for the equation of state parameters in the evolving dark energy model. designated W0 WACDM, came out as W0 equal to negative 0.5, 5 plus or minus 0.39, and WA equal to negative 1.32 plus or minus 0.79. Those numbers, taken at face value, suggest dark energy was stronger in the past and has been weakening over time the opposite behavior from a cosmological constant, which by definition never changes. The fuel in the tank of the universe, it appears, does not burn at a constant rate. Sometimes it runs hotter, sometimes it runs cooler. The rule that governs its behavior over time is not yet known. The equation of state parameter W carries enormous physical weight. If W is greater than -1, dark energy falls into a category called quintessence, a dynamic scalar field. Similar in concept to the fields that drove cosmic inflation in the universe's first fraction of a second, that permeates all of space and slowly weakens over time. Quintessence is strange, but theoretically manageable. It can be incorporated into quantum field theory without producing logical contradictions. If W is less than -1, the situation is categorically different. That regime carries a name, phantom energy, and phantom energy does not simply accelerate the expansion of the universe, it escalates that acceleration without limit. The strength of phantom energy grows over time, becoming progressively more powerful, until it overwhelms not just cosmic distances, but gravitational bonds at every scale, the forces holding galaxy clusters together, the gravity-binding solar systems, even the molecular bonds holding matter itself intact. The DESI data suggests that W may have crossed below -1 in the past, that dark energy may have briefly entered phantom territory before returning closer to the cosmological constant value. That crossing point has a name in theoretical physics, the phantom divide. It is a boundary that no simple single scalar field can cross while remaining physically consistent. Crossing it requires either two interacting fields, a model called quintom, or modifications to gravity itself on cosmological scales. The connection to the Hubble tension is not coincidental. If dark energy was stronger in the early universe than the cosmological constant model assumes, the expansion history of the cosmos was different. The sound horizon the standard ruler used to calibrate both the CMB and the baryon acoustic oscillation measurements would have a different physical size. A different sound horizon changes the Hubble constant extracted from the CMB. Early dark energy models have been proposed specifically as a mechanism for resolving the Hubble tension, and the DESI results, if confirmed at higher significance, would provide direct evidence that dark energy's evolution is precisely the kind needed to close at least part of that gap. DESI Year 2 data, covering a substantially larger galaxy sample, is expected to reach 4 to 5 sigma significance if the trend holds. That would cross the conventional threshold for a confirmed discovery. The cosmological constant Einstein's blunder turned cornerstone may be about to be overturned by the precision instruments of the 21st century. Einstein added it, removed it, and called it his greatest mistake. It came back. Now it is not just back, it is shape-shifting. If Einstein were alive to see the DESI results, he would probably find them equal parts amusing and infuriating, and he would almost certainly want to throw something. Dark energy is unstable, that alone is alarming enough. But when physicists looked more carefully at the data, they found evidence that it had once crossed a boundary that nothing in the universe is supposed to be allowed to cross. Dark energy, in its most familiar form, is almost peaceful in its violence. The cosmological constant W equal to -1 pushes the universe apart at a steady, exponential rate. Galaxies drift away from each other. The distances between galaxy clusters grow. Over hundreds of billions of years, the universe becomes increasingly sparse, increasingly cold, increasingly quiet. It is a slow dissolution, not a catastrophe. The stars still burn. Atoms still hold together. Planets still orbit. The cosmos unravels at a pace so gradual, it barely registers as destruction at all. Call it the universe's version of a long, quiet retirement. Everything gently moving apart until the lights eventually go out. Quintessence is even gentler. If W is greater than -1, dark energy weakens over time. The acceleration of expansion gradually slows. The universe might eventually reach a state of near stasis, expanding, but barely, with distant galaxies frozen almost motionless relative to one another, cold, dark, but structurally intact at every scale. The molecular bonds holding matter together survive. The gravitational bonds holding solar systems together survive. Quintessence allows the universe to age without being torn apart. Both of these scenarios sit on the safe side of a specific boundary in the physics of dark energy. That boundary is the phantom divide, the line at W equal to -1, that separates dark energy behaviors that are theoretically manageable from one that is not. Cross to the other side, and the physics changes in a way that has no precedent in the observable universe. If W drops below -1, dark energy enters what physicist Robert Caldwell first described in a 2002 paper as phantom energy. The term was deliberately chosen. Phantom energy does not simply push galaxies apart at a constant rate. It grows stronger over time. The more the universe expands under phantom energy's influence, the more phantom energy there is, and the stronger the push becomes. This is a self-reinforcing escalation with no natural break. Unlike ordinary matter or even quintessence, phantom energy violates what physicists call the weak energy condition, one of the foundational constraints in general relativity that governs how matter and energy are permitted to behave in space-time. A universe filled with phantom energy is a universe running a physics engine that general relativity was never designed to accommodate. The consequences compound without limit. At first, phantom energy behaves like a stronger version of the cosmological constant. Galaxies drift apart faster than they otherwise would. Then, as time passes and phantom energy grows, the acceleration becomes extreme enough to overcome the gravitational bonds between galaxies within clusters. Clusters dissolve, then individual galaxies are torn apart, then stellar systems, then planets, then, in the final fraction of a second, before the singularity that ends all structure, every atom in the universe is pulled apart. Every proton and electron stripped from one another. Every nuclear bond shredded by an expansion that has grown infinitely strong in finite time. Caldwell called this endpoint the Big Rip. That scenario will be examined fully in its own account. For now, the critical point is this phantom energy is not simply a stronger version of dark energy. It is a categorically different physical regime with a categorically different fate attached to it. The phantom divide, W equal to -1, is the line between those two worlds. In physics, crossing it is the equivalent of breaking the sound barrier, except that instead of a sonic boom, the consequence is the eventual destruction of every structure in the observable universe. No simple theoretical model can cross the phantom divide and return. A single scalar field, the standard mathematical description of dark energy, cannot produce a W that moves from above -1 to below it and then back again without violating fundamental principles of quantum field theory. Specifically, phantom fields are plagued by what physicists call ghost instabilities modes that carry negative kinetic energy and cause the vacuum of space to decay catastrophically, producing an infinite cascade of particle pairs and antiparticles that would destroy the universe instantaneously. In practice, phantom energy, if it exists, must be handled with extreme theoretical care. This is where the DESI data arrives with its uncomfortable implication. The first-year results from DESI combined with supernova data from the Dark Energy Survey's 5-year sample, show best fit equation of state parameters of W0 equal to negative 0.55 and WA equal to negative 1.32. When you trace what those parameters imply about dark energy's behavior across cosmic history, evaluating the equation of state at different redshifts, the data suggests that at redshifts between approximately 0.5 and 1, corresponding to a period when the universe was between 6 and 9 billion years old, W may have dipped below negative 1. Dark energy may have crossed the phantom divide and then crossed back. A crossing and return, water spontaneously evaporating faster than thermodynamics allows, then returning to normal behavior with no explanation. That analogy understates the strangeness. Water breaking thermodynamic rules is bizarre. Dark energy crossing the phantom divide and returning is a violation of the foundational constraints of quantum field theory, the most precisely tested physical theory in history, and then somehow recovering without leaving a permanent trace. To accommodate this behavior theoretically, physicists have proposed a model called quintum, a portmanteau of quintessence and phantom. The quintum model requires not one, but two distinct scalar fields, one that behaves as quintessence when dominant, one that behaves as phantom when dominant, interacting in a way that allows the combined equation of state to move through the phantom divide without triggering the ghost instabilities that a single phantom field would produce. Quintum is mathematically viable. It has not been ruled out. It has also not been confirmed by any observation. It represents the kind of theoretical construction physicists build when data demands something that existing frameworks cannot supply. The measurement challenge is severe. Confirming or ruling out the phantom divide crossing requires measuring W with a precision below 1% across a range of redshifts. Current precision, even with the DESI first-year data, reaches approximately 5%. The signal is there at 1 to 2 sigma at redshifts near 0.5, but sigma levels in that range are consistent with statistical fluctuation. The conclusion is not yet firm. 3 instruments are expected to resolve this within 5 to 10 years. The Euclid Space Telescope, launched by the European Space Agency in 2023, was designed specifically to measure the dark energy equation of state with approximately 1% precision across a large survey volume. DESI's 5th-year data release will increase the galaxy sample by a factor of several, pushing the statistical significance substantially higher. And the Nancy Grace Roman Space Telescope, NASA's planned Wide-Field Infrared Observatory, will provide complementary supernova and weak lensing measurements that cross-check the dark energy equation of state through independent physics. Together, these instruments will either confirm that dark energy crossed the phantom divide, which would require rewriting quantum field theory at its foundations, or show that the current data is a statistical fluctuation, and dark energy is closer to the cosmological constant than DESI's first year suggested. In physics, crossing the phantom divide is roughly equivalent to driving through the speed of light barrier. Everything in the theory says it cannot happen, but the data is looking back at you with an expression that is very difficult to read as confident agreement. The answer is coming. The instruments are already in space. The question is whether the universe will cooperate by making the signal cleaner, or whether it will do what it has done at every step of this story, reveal something stranger than the framework built to contain it. Dark energy is changing and may once have crossed a boundary nothing in the universe is supposed to cross. But that chaos does not only exist at cosmic scale. Right in our own galactic neighborhood, violence is unfolding in ways we tend to forget when we look up at a quiet night sky. Step outside on a clear night, away from city lights, and look up. What you see feels permanent. Still, the stars appear fixed in their constellations, exactly where they were last night and last year, and 1,000 years ago when the same patterns guided sailors across the Atlantic. The universe, from down here, looks like the very definition of peace. That stillness is an illusion produced entirely by the inadequacy of human timescales against cosmic ones. The universe does not build by sitting quietly. It builds by collision, explosion, and destruction on scales so extreme that the word violent barely begins to serve. Every structure in the observable cosmos, every galaxy, every star cluster, every planetary system was forged through processes of catastrophic energy release and matter redistribution. There is no gentle alternative. The universe has never offered one. 3 examples demonstrate this, each one larger and more extreme than the last. The first involves a star and a black hole, and it begins with something called the Hill's mechanism. When a binary star system, 2 stars orbiting each other, passes close enough to the supermassive black hole at the center of a galaxy, the gravitational tidal forces from the black hole can be strong enough to separate the pair. One star gets captured into a tight orbit around the black hole. The other gets catapulted outward with an enormous velocity boost, carrying the orbital energy that the pair previously shared. The result is a hypervelocity star, a single star moving fast enough to escape the gravitational pull of the entire galaxy. Warren Brown and colleagues first confirmed the existence of hypervelocity stars in 2005. The velocities involved are extraordinary. These stars move at up to 1,700 kilometers per second, not kilometers per hour. Per second, that is approximately 6 million kilometers per hour. Fast enough to cross the entire width of the continental United States in a fraction of a millisecond, more than enough to escape the Milky Way entirely, leaving the galaxy on a trajectory that will carry them through intergalactic space forever. The Gaia Space Telescope and Webb are currently collaborating on a catalog of confirmed hypervelocity stars, with more than 20 cases confirmed to date. These are not rare accidents. They are a regular output of the machinery operating at the center of our own galaxy, running continuously, ejecting stars into the void at millions of kilometers per hour on a timescale of thousands of years. Imagine firing a bowling ball from the center of a city with enough force that it punches through the atmosphere and keeps going. The mechanics are different. The sense of scale is the same. The second example is closer to home, disturbingly close. The Andromeda Galaxy, also known as Messier 31, is the largest member of our local group and the Milky Way's nearest major neighbor at approximately 2.5 million light-years. It is also approaching us. Proper motion measurements from the Hubble Space Telescope and confirmed with extraordinary precision by Gaia's 3rd data release show Andromeda closing the distance at approximately 110 kilometers per second. Cox and Loeb modeled the collision in 2008. The first close passage is expected approximately 4.5 billion years from now. The merged galaxy has already been given a name, Milkomeda, or sometimes Milkdromeda, depending on who is doing the naming. The collision sounds like the end of everything. It is not, precisely. The space between individual stars within both galaxies is so vast measured in light-years, not kilometers, that the probability of any 2 stars physically colliding during the merger is extremely small. The galaxies will pass through each other largely as 2 collections of empty space with stars distributed throughout, drawn together by the gravity of their dark matter halos rather than by direct stellar impacts. Most stars, including the Sun, will survive the merger structurally intact, though likely scattered into different orbital configurations within the resulting combined system. The Sun may end up at a substantially different distance from the new galactic center than it currently occupies. Earth's orbit around the Sun is expected to remain stable throughout. What will not remain stable is the pair of supermassive black holes at the centers of both galaxies. As the galaxies merge, the black holes will spiral toward each other through a process called dynamical friction, gradually losing orbital energy until they reach separations of a few light years. At that point, they begin producing gravitational waves, ripples in space-time of a power and frequency utterly unlike anything LIGO has detected from stellar mass black hole mergers. Eventually, the two black holes merge. The gravitational wave burst released in the final coalescence would be, by several orders of magnitude, the most energetic single event in the local universe since the Big Bang. The third example takes place right now, 280 million light-years away, and Webb has captured it in unprecedented detail. Stephan's quintet, officially designated Hickson Compact Group 92, is a group of 5 galaxies in close gravitational interaction in the constellation Pegasus. 4 of the 5 are genuinely interacting at similar distances. The fifth, NGC 7317, is a foreground object at a much closer distance that happens to lie in the same line of sight of the 4 genuinely interacting galaxies. One NGC 7318b is currently plunging into the group at approximately 800 kilometers per second. That inflow velocity is producing a shock wave, a plasma shock wave stretching approximately 100,000 light-years in extent, larger than the Milky Way running through the intergalactic medium between the galaxies. Webb's near-infrared camera and mid-infrared instrument captured this shock wave in 2022, in detail no previous telescope could achieve. The shock front is superheating gas to temperatures exceeding the surface temperature of the Sun, producing intense X-ray emission visible across the group. Within that shock, Webb detected emission from molecular hydrogen, carbon monoxide, and a range of complex molecules chemistry being driven by the kinetic energy of a galaxy collision, synthesis occurring inside violence rather than despite it. That last point carries the philosophical weight of the entire pattern. Without supernova explosions, no heavy elements exist. Without heavy elements, no rocky planets form. Without rocky planets, no biospheres develop. Without galaxy mergers, triggering new waves of star formation. Mature galaxies exhaust their gas supply and stop producing new stars, aging passively into red ellipticals with no capacity for further chemical enrichment. The violence is not incidental to the story of cosmic structure. The violence is the mechanism. Destruction and creation in the universe are not opposites. They are the same process observed at different moments. The Sun sits in an unusually quiet region of the Milky Way, a stable position in the outer disk, away from the turbulent, star-forming regions of the spiral arms, away from the black hole at the center. It has held that position for approximately 4.5 billion years. That stability is not the norm. It is statistical good fortune, a quiet backwater in a cosmos that builds everything it has ever made through collision, catastrophe, and the slow rearrangement of wreckage into something new. The universe does not create beautiful things by sitting still. It creates them by slamming everything together hard enough and long enough to see what survives. Collision and destruction, that is the language the universe uses to build. But just when we thought we understood the rules, James Webb revealed structures so enormous that their very existence violates those rules entirely. Every equation that describes the universe rests on one assumption so basic that almost nobody outside cosmology has ever heard its name. And yet without it, the entire mathematical structure of modern astrophysics falls apart. That assumption is called the cosmological principle. It states that, at sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means roughly the same amount of matter is spread through every large region of space. Isotropic means the universe looks the same no matter which direction you point a telescope. The accepted threshold for this smoothing out sits somewhere between 300 million and 400 million light-years. Beyond that scale, According to the principle, all the clumps, filaments, and voids average out into a uniform cosmic soup. This is not a side note buried in an appendix. The Friedmann equations, which describe how the universe expands and evolves over time, are derived directly from this assumption. Lambda CDM is built on top of the Friedmann equations. Every calculation of the age of the universe, every prediction about expansion, every model of how galaxies and structure formed assumes that no region of space is special, and that any large enough volume looks statistically the same as any other large enough volume, anywhere. Picture trying to calculate the average temperature of an entire continent. You cannot take a single reading in one city and call it done. You need enough sample points, spread widely enough, that local extremes cancel out into a meaningful average. The cosmological principle makes the same claim about the universe. Sample a region a few 100 million light-years across, anywhere in the cosmos, and the lumps should disappear into a smooth average. In 2014, and again in an updated analysis in 2023, Lajos Horváth and colleagues published evidence for something that should not exist if that principle holds. They identified a structure now called the Hercules Corona Borealis Great Wall, mapped through the distribution of gamma-ray bursts at redshifts between 1.6 and 2.1. Its dimensions are staggering, roughly 10 billion light-years across in one direction, and 7.2 billion light-years in the other. That makes it the largest known structure in the observable universe. Full stop. 10 billion light-years is not just large. It exceeds the theoretical homogeneity scale of the universe by a factor of roughly 8 to 10 times. If the cosmological principle is correct, a structure of that size simply should not be able to form. There has not been enough time since the Big Bang for gravity, working at the speed it works, to gather matter into something that big. And if the structure is real, the consequences are not contained to one strange object sitting far away. Every equation built on the assumption that the universe evens out at smaller scales would be standing on ground that does not actually exist. The Hercules Corona Borealis Great Wall is not alone. In 2003, astronomers using data from the Sloan Digital Sky Survey identified the Sloan Great Wall, a structure spanning approximately 1.37 billion light-years, itself already larger than the homogeneity scale predicts. In 2022, Alexia Lopez and colleagues identified another enormous structure called the Giant Arc, traced through the absorption signatures of magnesium ions in quasar light, spanning approximately 3.3 billion light-years, with a statistical confidence of 99.7%. None of these are isolated curiosities. They form a pattern, and the pattern points in one direction. There is an important caveat, and it matters. Gamma-ray bursts are not a perfect tracer of where matter sits in the universe. They come from the deaths of massive stars, and massive stars are not distributed in a way that maps cleanly onto the overall mass distribution of the cosmos. It is possible that the Hercules Corona Borealis Great Wall is, at least partly, a statistical artifact, an illusion created by an uneven sample of cosmic explosions rather than a true map of where galaxies actually sit. Confirming or ruling it out requires a direct survey of galaxies themselves at the same redshifts, with enough depth and coverage to settle the question. This is precisely the kind of survey Webb is built for. Its ability to map galaxies at redshifts between 1.5 and 2.5 across wide fields and with spectroscopic precision gives astronomers a tool that did not exist when Horváth's team first published their results. Within the next 5 years, Webb should be able to either confirm the Hercules Corona Borealis Great Wall as a genuine structure, or reveal it as a statistical mirage built from an unlucky distribution of exploding stars. And if it is confirmed, the problem does not end with This is a big structure. Cosmologists would then have to explain how a structure of that size formed at all, given how little time the universe has had since the Big Bang under standard theory. Gravity is slow. Assembling something 10 billion light-years across, even with billions of years to work with, pushes against the limits of how fast matter can be gathered by gravitational attraction alone. The deeper issue reaches all the way down to the foundations. If the cosmological principle fails at these scales, the Friedmann equations rest on a false premise. And if the Friedmann equations rest on a false premise, lambda CDM is not just missing an ingredient. The way it appeared to be in earlier parts of this story would be built on the wrong floor plan from the very start. Alternatives exist, though none of them are simple. One option is an anisotropic universe, one that genuinely does look different in different directions at the largest scales, something the standard model explicitly forbids. Another is a class of solutions called Bianchi models, which allow for universes that expand at different rates along different axes. And there are possibilities that do not yet have names, frameworks that have not been written down because nobody expected to need them. There is one more thread that connects to all of this, and it comes from the oldest light in the universe. The cosmic microwave background has a dipole, a slight temperature variation across the sky that is normally explained entirely by our own motion through space. But in 2022, Nathan Seacrest and colleagues found that the distribution of distant radio galaxies and quasars across the sky has its own dipole, and it points in roughly the same direction as the CMB dipole, but with more than twice the strength it should have if our motion were the only cause. The tension between the expected and observed dipole reaches 4.9 sigma. Something about the large-scale distribution of matter in the universe may not be as even as the standard model requires. And two completely independent lines of evidence, one from gamma-ray bursts and quasar absorption, one from the oldest radiation in existence, both seem to be pointing at the same crack. Cosmology has one foundational principle. The universe is supposed to look the same in every direction. The universe, apparently, never read that principle. The data is precise. The Hercules Corona Borealis Great Wall, identified from 283 gamma-ray bursts, the theoretical homogeneity scale, around 1.2 billion light-years, according to Yadav and colleagues in 2010. The giant arc, 3.3 billion light-years, confirmed at 99.7% confidence. The radio dipole, more than twice the strength of the CMB dipole. A tension of 4.9 sigma. These colossal structures break the model. And if that model is wrong, then our predictions about the future of the universe, about the death of everything, could also be wrong. Or worse, reality could be even more extreme than anything we've predicted. Every civilization that has ever looked up at the night sky has asked the same question in some form. How does this end? Religions built entire cosmologies around the answer. Philosophers debated it for millennia without a single piece of data to test their ideas against. For the first time in human history, that question is no longer purely philosophical. Modern cosmology can answer it with numbers, with equations, with actual measurements taken by actual instruments orbiting a small planet around an ordinary star. Anyone who has lived long enough to watch empires fall, technologies vanish, and certainties dissolve into something unrecognizable, already understands, on some level, that nothing lasts. The universe is no exception. The only question is which ending is coming, and cosmologists have narrowed it down to three. The first scenario is called the Big Freeze, sometimes referred to as heat death. This is what happens if dark energy behaves exactly as Einstein's cosmological constant predicts, with W equal to -1, constant and unchanging forever. Under this scenario, the universe simply keeps expanding, slowly and steadily, For an unimaginable length of time, galaxies drift further apart. Stars burn through their fuel one by one and go dark. By around 10 to the 14th power years from now, the last stars still capable of nuclear fusion will have exhausted their fuel entirely. By around 10 to the 40th power years, the black holes that remain will have consumed nearly everything else within reach. And somewhere between 10 to the 67th power and 10 to the 100th power years, even those black holes will have evaporated completely through the slow process of Hawking radiation, releasing their mass as a thin mist of particles and photons. What remains after that is close to nothing, a cold, dark, expanding sea of light with no stars, no planets, no structure of any kind, and no way for information to be transmitted or stored. Physicists call this state of maximum entropy the heat death of the universe. The second scenario is the Big Rip, and it is the most violent of the three. This is what happens if dark energy is phantom energy, with W less than -1, and if that value does not change over time. Phantom energy grows stronger as the universe expands, which means the expansion itself accelerates without limit, faster and faster, until it begins tearing apart structures that gravity has held together for billions of years. Robert Caldwell and colleagues worked out the timeline for this scenario in 2003, and the sequence is almost unbearably specific. 200 million years before the end, the Milky Way itself would be torn apart, its stars ripped from their orbits around the galactic center. 3 months before the end, the solar system would be destroyed, planets flung away from the sun as the expansion overwhelms gravity at that scale. 30 minutes before the end, Earth itself would be torn apart, and in the final 10 to the -19th power seconds, atoms themselves would be ripped apart, nuclei torn from electrons, protons and neutrons shredded into their constituent particles. If the equation of state parameter dewey sits at approximately -1.5, this entire sequence would arrive in roughly 22 billion years. The third scenario is the Big Crunch, and in some ways it is the most familiar because it mirrors the Big Bang in reverse. This would happen if dark energy, instead of remaining constant or growing stronger, weakens over time and eventually reverses direction entirely, turning from a repulsive force into an attractive one. Under this scenario, the expansion of the universe would slow, stop, and then reverse. Everything that has spent billions of years moving apart would begin moving back together, faster and faster, collapsing toward a single point. Temperatures would climb without limit as matter and radiation were compressed into smaller and smaller volumes, ending in a singularity, the mirror image of the one the universe began in. Current data from Type 1. A supernovae makes this scenario look unlikely, though models that allow dark energy's equation of state to change over time have not ruled it out entirely. Whichever of these three turns out to be true, there is something else worth sitting with, something that has nothing to do with which ending arrives, and everything to do with when we happen to be alive to ask the question at all. The universe is roughly 13.8 billion years old. Galaxies needed time to form, stars needed time to ignite, and it took billions of years before a universe full of light settled into something resembling the night sky we recognize. But the universe is also expanding, and that expansion is accelerating. Eventually, distant galaxies will cross beyond what is called the cosmic horizon, the boundary past which their light can never reach us again, no matter how long we wait. Abraham Loeb calculated in 2002 that within roughly 2 billion years, expansion will have removed 99% of the galaxies currently visible to us from any possibility of future observation. And within roughly 2 trillion years, essentially every galaxy beyond our immediate local group will have vanished past that horizon entirely. A civilization that evolved late enough, in a universe 2 trillion years old, would look up and see only its own galaxy, isolated against a featureless black sky. No cosmic microwave background to study, no distant galaxies to measure redshift from. No evidence that the universe had ever expanded, ever had a beginning, or had ever contained anything beyond the small island of stars surrounding them. They would have no way of knowing any of this had ever happened. We exist in a narrow window, late enough that galaxies have formed and stars have ignited, and life has had time to evolve and build telescopes, but early enough that the light from the deep past and the structure of the universe at the largest scales is still visible to us. We are the generation that can read the whole book of the universe before the pages are torn out and drift away into darkness. If you are worried about the Big Rip arriving in 22 billion years, the good news is you will not be late for it. The bad news is that nothing else will be on time either. The data behind these three futures comes from decades of independent work. The Big Freeze scenario was worked out in detail by Fred Adams and Gregory Laughlin in 1997 in a paper published in Reviews of Modern Physics. The Big Rip timeline comes from Caldwell, Kamiankowski, and Weinberg in 2003, with a rip time of approximately 22 billion years if W equals approximately -1.5. The Big Crunch remains disfavored by Type 1a supernova data, though not fully excluded within models that allow the equation of state to evolve over time. And the calculation of how much of the observable universe will eventually vanish beyond our cosmic horizon comes from Abraham Loeb's 2002 analysis, showing that within 2 billion years, 99% of the galaxies we can currently observe will become permanently unreachable. We started with a mirror coated in gold, parked 1.5 million kilometers from home, and ended somewhere far stranger. Galaxies that grew up too fast, oxygen that arrived too early, black holes that broke every ratio we thought was fixed, voids the size of nations of galaxies, a void we might be living inside, a constant that may not be constant, a universe that may not look the same in every direction, and 3 different ways everything could eventually end. The universe is 13.8 billion years old. Webb has been watching it for barely 2 years. That is something like reading 2 pages of a 500-page book and already finding contradictions on every line. Every answer Webb hands back seems to open 10 new questions behind it. That is not failure. That has always been how discovery works, and it is how it is supposed to work. For the first time in human history, a generation can look back toward the birth of everything and ask serious questions about its death. The dark is not the end of the story. It is an invitation, and James Webb is lighting it up, one corner at a time. We are not near the end of this. We are only just beginning.